Hi everyone, and welcome to the second of two narrated PowerPoints covering geologic structures. In this PowerPoint, we're going to focus on folds and joints. So what is a fold? Quite simply, a fold is a ductile bend in layered rock. The layered rock could be sedimentary rock. The layered rock could be foliated metamorphic rock. The layered rock could even be successively stacked lava flows. And if the bend in the rock is arching upward, we call that type of upward arching fold an anticline. If the bend in the rock is arching downward, we call that downward arching bend a syncline. We won't worry so much about monoclines in this class. So what's an easy way to remember the difference between an upward arching anticline and a downward arching syncline? Well, for me, I associate anticline with the letter A, and if you were to move up and over the letter A, you'd sketch out an anticline. Likewise, I associate syncline with the word sink, and when I think of a sink, I think of a basin, and there's my downward arching fold, looks like a smile. So whatever you need to do to remember that, just make sure you can distinguish anticlines and synclines based on their shape. What are the stress-strain relationships associated with folds? Well, because folds fundamentally represent permanent bends in the rock, that's got to mean that they're illustrations, they're manifestations of ductile strain behavior, like when you take taffy and twist it, or you take silly putty and stretch it. The bending in this case is permanent, but we haven't ruptured the rock. So we have ductile strain behavior, not elastic and not brittle strain behavior in the case of all folds. The simplest type of stress to imagine associated with folding is like we see in this upper left diagram, regional compressive stress. But I will say in passing that any kind of stress can produce folding under the right conditions, including tensile stress and also shear stress. Here's some quick examples, some cross-sectional photographs of anticlines and synclines. So in the case of our anticline, there's that letter A, go up and over the letter A, and you get an anticline. Over in the right-hand diagram, again, imagine a sink full of water, and the basin holding the water defines a syncline. And then in the middle diagram, we have a nice example of an anticline-syncline pair. And that's very common, by the way. Typically, folds tend to occur in multiples. Also, as we'll see a little bit later on in this presentation, folding in general tends to occur down deep because it's down deep where we find the right conditions to produce folding under the right kind of stress, namely warmer temperatures and higher pressures. Under such conditions, the rocks will tend to bend rather than break, and so we'll get folding rather than faulting at depth. So what are the different parts of the fold? Well, you can imagine the sides of the fold and the middle of the fold, as you can see on this diagram. So the sides of the fold are referred to as the limbs of the fold. Imagine sticking your arms out to the side, away from you. You're sticking out your limbs. The middle of the fold, where in effect the fold is the most bendy, that's known as the hinge region of the fold. So make sure you can distinguish the limbs and the hinge of anticlines and synclines. Beyond that, how do we describe the three-dimensional orientation of folds in space? We typically do it using the concepts of axial plane and fold axis. Think of the axial plane as an imaginary plane of symmetry that bisects the fold, that is, chops it into two more or less equal mirror images. You can't see axial planes, but you can imagine them in your mind. Likewise, a fold axis can be thought of as a line of symmetry rather than a plane of symmetry that bisects the fold. And the reason we often like to describe the orientation of a fold in terms of its axis is that that's a convenient way to communicate that orientation on a map. And then again, the very middle of the fold, where in effect the fold is the most bendy, where it flips over from dipping one direction to dipping another direction, that's called the hinge of the fold. So let's get some practice recognizing the different parts of a fold and describing the orientation of folds. Here we're looking at a cross-sectional diagram of a syncline. We know that because it's a downward arching fold, like a basin. So how about this second question? What's the dip angle of the axial plane of the fold? Well, again, we can't see the axial plane of the fold on the photograph. We have to imagine it. And to help you visualize the axial plane of this fold, I've added this diagram. So that blue vertical plane chopping the syncline into two mirror images, that's the axial plane. Remember too that dip refers to downward tilt. And so in this case, the dip angle of the axial plane of the fold is 90 degrees. That's just another way of saying that the axial plane is vertical. How do we reference dip angle? We always reference dip angle with respect to an imaginary horizontal plane running across the fold. What I've just drawn isn't a horizontal plane because I don't have that third dimension to work with. Instead, what I've drawn is the intersection that the horizontal plane makes with the photograph. So again, you have to use your imagination a little bit. And that's going to be my 0 point for measuring the dip angle, in this case, of the axial plane. And you can see in this diagram down here that dip angle is 90 degrees. Again, if my plane is vertical, then the dip angle is going to be 90 degrees. If my dipping plane is flat, if it's horizontal, the dip angle is going to be 0 degrees. And if my dipping plane, whatever it is roughly halfway in between being flat and vertical, that would be a 45-degree dip angle. So in this case, if we focus on the northeastern limb of the fold, we're really talking about this limb right here. That's the northeastern side of the fold. And we recognize the limb based on the bedding in the layers that are folded in that northeastern limb. And notice that those layers, as you see here, make about a 40-degree angle with this imaginary horizontal plane. So clearly, the northeastern limb of the fold, it's not flat, so it's not dipping at 0 degrees, but nor is it vertical. It's not dipping at 90 degrees. In fact, it's dipping at a dip angle of 40 degrees. What about the dip direction of the northeastern limb of this fold? To do that, we just have to imagine what compass direction the northeastern limb of the fold is tilted downward toward. Downhill is not a compass direction. A compass direction is always going to be a point of the compass, north, south, east, west, northwest, southeast, etc. So right away, if you see a photograph like this and I ask you about the dip direction in cross-section, it's either going to be this or this. And a good sort of simple way to get the dip direction is to imagine a ball, in this case, rolling down the limb of the fold, the northeastern limb. And as the ball rolls downhill, it eventually enters the hinge of the fold. And for a moment there, the ball is actually rolling horizontally. And so we just ask ourselves, well, what direction is the ball rolling at that point? It's rolling toward the southwest. So that would be the dip direction of the northeastern limb of this fold. So hopefully that makes sense. I didn't ask you this on the diagram, but what if I were to ask you, what is the dip direction of the southwestern limb of the fold, what I've just circled? Well, the dip direction of the southwestern limb of the fold is going to be northeast. And again, an easy way to kind of visualize that is, in your mind, draw your ball, let the ball roll down towards the hinge region of the fold, and where the ball flattens out, we just ask ourselves which direction is the ball rolling at that point. It's rolling toward the northeast. So that is to say that in this case, the southwestern limb of this fold is dipping toward the northeast. Here's a cross-section of an anticline, and all I want you to appreciate here is that for an anticline in particular, the rock changes relative age along the surface of an eroded anticline. Notice that if you stand on the limb of this anticline, the rock is a certain age. You can see the pattern there. And then if you were to walk in towards the hinge region of the anticline from here to here, then by the time you get into the hinge of the anticline, you're standing on that rock layer. So imagine now if you could unbend the fold in your mind, you can probably appreciate from all this that this rock layer exposed in the hinge region of the fold at the ground surface is older than this rock layer exposed along the limb of the fold at the ground surface. So the overall pattern then is that as one moves from the limbs of an anticline in towards the hinge of the anticline, that's where we find the oldest rock exposed at the ground surface. Another way of saying that is that the rock gets older as one migrates from the limb into the hinge of an anticline. It's actually the opposite for a syncline, as you can demonstrate yourself. When one migrates at the ground surface from the limbs of a syncline into the hinge of the syncline, the rock becomes younger at the Earth's surface. This slide is just meant to demonstrate where in general folding and faulting dominate. So if we're up near the Earth's surface, generally at depths of less than 10 kilometers, the rock tends to be relatively cool and not under much pressure. And so under tectonic stresses, it behaves in more of a brittle fashion. And it's that brittle strain behavior that characterizes faults. On the other hand, if the rock is deeper, generally below depths of 10 kilometers or so, it's much more likely to behave as a plastic solid, meaning that when stressed, when subjected to regional compressive tectonic stress, for example, any layered rocks, in this case, looks like gneiss, a foliated metamorphic rock, layered rocks at those depths, because they're under higher temperatures and higher pressures, are more likely to strain in a ductile fashion, producing folds rather than faults. Okay, on to joints. Very briefly, joints are fractures that don't show evidence of slippage across the fracture, whereas faults do show evidence of slippage across the fracture. So what we're looking at here in this cross-sectional photograph is jointing rather than faulting. The yellow dashed lines represent bedding planes that I've drawn. So that's sedimentary bedding, and then you can pretty clearly see the cracks here, 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 etc. And notice especially that across a single crack, we don't see any shifting or offset of the sedimentary layers. As far as we can tell, the sedimentary layers appear to be continuous across the cracks. So that's what makes these cracks joints as opposed to faults. And then one final example of some rather dramatic jointing I'll show you is called columnar jointing. And columnar jointing arises due to shrinkage of igneous rock as it cools and crystallizes. And so what we're seeing in the top diagram, imagine that this is a lava flow or perhaps a shallow horizontal sheet-like intrusion of magma. As the magma cools, if it cools under appropriate conditions, then it'll shrink and shrinkage cracks will develop, whereby every point within the cooling magma pulls away from every other point. And the result under the right conditions is to get these polygon-shaped cracks that extend vertically downward in this case. And they help define, in this case, in the case of the top diagram, vertical columns that would look somewhat similar to that right-hand photograph. So that's B. In A, we're looking at a vertical intrusion defined by the blue line. That's a dike. It's a vertical intrusion that cuts across the structural grain of the surrounding rock. And the rule with columnar joints is that the joints always develop at a 90-degree angle to the cooling surface. So if the cooling surface is horizontal, then the joints tend to be vertical, as we're seeing in B. On the other hand, in A, the cooling surface itself is vertical, and so the joints, the columnar joints, tend to be horizontal. And then in C, we're actually looking at a feature called a lava pillow. And a lava pillow is just sort of a bulbous blob of lava that forms underwater, in this case in Iceland, underneath a glacier. And so in C, we have a round cooling surface. And the rule of thumb is that the joints, the columnar joints, the shrinkage cracks, always develop at a 90-degree angle to the cooling surface. And so in C, because the cooling surface is round, the joints form like spokes of a wheel. Here are a few more dramatic examples of columnar jointing. This happens to be along or very near the southern tip of Iceland at the backside, along the backside of a black sand beach. This is basaltic sand on the beach. And in back of the beach is a really tall sea cliff characterized by some of the best columnar jointing on Earth. It's really incredible. You get 4-sided and 6-sided and 5-sided and even 3-sided joints. And then right here, if you stand right here and sort of look up at the roof of this cave, you can actually see the undersides of these columnar joints. Okay, so that's it. I think we'll wrap things up.